Hey, thanks for everyone for coming out Tuesday night to come to talk about C++. I'm excited to talk to you about code indexing at Meta a little bit today. The system is called Glean. It's a brand new system that most of you probably have never heard of or seen, and so it's going to take a little bit of work to kind of bring you up to speed as to to build a foundation. But ultimately, I want to get to kind of the nasty C++ bits that you probably came to see. So let's get started. So this is a quick agenda I have for us today. Very quick motivation. We're going to go through a brief architecture overview of Glean. I'm going to introduce Angle, which is the schema defining and query language that we have for the system. And then we'll talk about handling C++ macros, which hopefully we'll get to. Okay, so the first motivation. The motivation essentially is for us to be able to provide delightful developer tools. So there are a bunch of tools that we use probably on a day-to-day basis. This, for example, is an example is from CppBayArea, where it provides go-to-definition operations from a declaration to the corresponding definition and then going back, right? There are also tools like web-based code browsers, like they have on GitHub. And this one, for example, is providing information about this capacity variable with its type, corresponding documentation, which is fetched from the header where the declaration is, list a bunch of references to this variable and stuff like that. We also have documentation generation tools, right? This also goes to look at your code, analyzes it, puts together documentation for you. And all of these tools kind of do similar things. And so, but they have various limitations, and we'll get to those. We have a lot of these, right? So we have IDEs, code browsers, documentation generation that I just showed, but there's also like symbol search kind of stuff. So if you wanted to ask your system, like, oh, where are the variables that are named size, right? grep will get you all of the places that mention size, but is it going to get you the places where the variables are named size? Code analysis tools like linters, dead code detection, and last one is a little bit lesser known, but having API usage tracking for library developers would be super useful to be able to deprecate a function, introduce a new one, and you kind of see a graph of downward trends of deprecated functions. So you can kind of gauge like, okay, which of these look reasonable for me to like do it by hand and just get rid of at this point, right? And now what typically happens is you try to get rid of it, put it on some build farm, and then see what breaks, right? And you can't just kind of quickly scan through like what candidates are reasonable to try to get rid of. And so, yeah, there are various limitations. Some of these tools are language specific. CppBayArea, for example, is a great tool, but it works for C, C++, Objective-C, right? Some tools are language agnostic, like the documentation tool, but a lot of them end up having like missing language specific details. Scaling to large code bases can be often challenging. So if you've used like local IDEs and you work on a large code base, you might be waiting a long time for it to finish indexing before you can actually start doing stuff. And then, of course, by the time it's finished indexing, you're going to modify the code, and then you're going to wait again, right? So the development cycle gets really, really frustrating when it doesn't scale. The other point is the collected data by all these tools are not generally available for you to query, right? Like your documentation tool, for example, went and looked at all of your functions and got the documentation for those functions, right? So it has the information to tell you how many out of all my functions have documentation, right? So you could have a metric of like, 60% of my functions are documented or something like that, but it doesn't provide that API, right? You could maybe like hack something into Doxygen directly to like give you that information. But like the information that this tool saw, it doesn't really provide to you. So scaling up, we want to scale up in several different axes. One is to support many languages. We want to be language specific as well as language agnostic. We want to be able to scale to large code bases, such as the giant monorepo that we have at Meta. We want to be able to power many developer tools like the ones that we just went through and more, and be able to serve complex queries. Complex and flexible queries. And the schema in which we collect this data, we want to be able to extend so that we can collect more data when we realize different use cases and needs. So this is where it brings us to Glean. And Glean is effectively a code indexing platform for all the different languages that we're going to support. And we'll go through an architecture review overview of this. Okay, so we have Glean in the middle, and it's essentially a database of key value stores, kind of the core basis of it, right? We're going to have all these languages that we want to support: C++, Hack, Haskell, and JavaScript, let's say. And we're going to use the native language front ends for all of these languages. So C++, Clang is kind of the go-to tool for that. Hack, well, we own the compiler for that, so that's no problem. Haskell has a tool that dumps the ASTs. JavaScript has its own thing as well. And so we're going to use these native front ends because we're not going to try to approximate these languages because we're surely going to miss something if we do that. And then we're going to then send a bunch of data to Glean to collect all of that. Glean will then, and these collectively are the indexers, right? And we're going to, typically what happens for us at least is the specific language foundation teams will own the indexers because they're the experts in those languages anyway. And so for me, I own basically the C++ indexer so that we can provide rich information to Glean that we can use for, well, we'll see, well, for developer tools to be built on. So all this data is going into RocksDB, which is the storage backend for Glean. We're going to write that data. And then that's the storage layer, of which I'm not going to say anything about. Just treat that as a black box. It's not really important to this discussion. OK, on the right, we have all these tools that we've already seen, right? And all of them are going to query Glean for whatever information that it wants to use to serve its purpose. Glean will then read the information that it wrote to RocksDB and serve the responses. OK. So, and these are our clients. And so in the middle of it, we need to be able to communicate with all of the indexers and also to all of the clients, right? And so that brings us to the need of a schema because we need some protocol to be able to communicate in between these different components. But Glean doesn't enforce a single schema. If you've seen systems like this before, typically they'll have a single schema that you need to basically conform to. And I'll get into what those details just after this. But basically, the reason for not providing a single schema is because each language has their own nuances and specifics. C++ has plenty of those, right? And different clients need different data, even for the same language. And I'll give a specific example of what I mean by that. So for a single schema, typically what happens is you end up providing like the least common denominator of all the different languages, right? So the idea is, well, all these variable declarations in all these different languages are subtly different with like qualifiers and different keywords and such, but like at the end of the day, they're still variable declarations. It's fine, right? All these different languages have classes and notion of inheritance. Yeah, syntax is different, but like classes and inheritance, we can do that, right? And so you define some common denominator of all of the languages, and then you use that to serve your clients. And so, for example, a code browser could use this and say, oh, when I click on this thing, go to that location. And you can kind of do that across different languages without like all that much language specific information, and you'll be fine. But what if you want to build language specific tools, right? So if you wanted to try to do dead include removal for C++, and trying to use a schema like this, you're going to have a bad time. And the reason I can say that quite confidently is because in previous attempts of building this tool, like include what you use, or in the latest iteration in Clang, it's called include cleaner. Those tools still struggle with full-fledged Clang AST information, right? So if you try to build that tool off of something that's trimmed down, you're not going to have a good time. The other approach is to just go with a big schema, right? Just union all of the features across all the languages And you can, yeah, well, this will serve everything, right? The problem, of course, is all of them, like there's going to be a bunch of comments. It's going to be a giant schema to begin with. And then within those schemas, you're going to have parts where it's like, oh yeah, this is only for C++, static, C, C++, const, C, C++, const expr, C++ only, right? It like this thing Java only, this thing Haskell only, blah, 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 right? It's going to be a really difficult schema to work with given something like this. So what does Glean offer? We're going to split this up. We're going to split this up into multiple schemas. We're gonna support a schema per language, and the shield looking thing in the middle there was the intersection of the Venn diagram. So that's going to be our code markup layer, and so that's going to be effectively our language agnostic layer, which we can derive from the language specifics, and we'll get into like concretely how we do that. And now the code, like something that's language agnostic, like code browser, can hit the code markup layer, and something like that include removal for C++ can query the C++ specific schema, right? Okay, so this is the example where different clients want different data. So we're talking about the same language, we're talking about C++, and suppose we're trying to write a static analysis tool versus a code navigation tool. Okay, so let's walk through the example a little bit, right? So we have namespace n, void foo. We have some function foo defined in namespace n. We have some horrible macro called n : foo. I'm sure you've seen code like this before. And then bar is going to effectively call that macro, which gets invoked, expanded to n : foo, right? So if we're being precise about what the language does, the AST that gets produced by this program on the left, the references are going to come from that expanded location, right? And this is like truly what happens, because inside the macro definition, they're just tokens. They don't have any semantic meaning, right? It doesn't have any semantic meaning until it's pasted somewhere. So once that thing is pasted, the references to n, the namespace n, and the function foo come from inside bar. And so you could do static analysis, for example, that say, hey, does bar call foo, right? And it'll say, yes, there's a reference to foo from within the body of bar. And so we can do that, make that deduction. But this isn't, but imagine if you like command clicked on macro and you got 3 options from the IDE saying like, you want to go to macro, n, or foo, right? You'd be like, take me to macro. What do you mean n or foo? Why are you even asking me that, right? And so code navigation really wants to do something like this, right? Where like you want to click on foo and go to foo, even if it's within the macro, depending on how it's like, if it's used in such a way that it's going to take you there, right? And so there's this desire for different clients, even for the same language, that want quote unquote same data. Like I just want cross references from C++. You still want slightly different cross-references depending on what you're building. And on the right, you might actually ask, well, like, are these just kind of like functions where like if bar calls macro and macro calls foo, then transitively bar will call foo, right? The problem is macros are much more evil than functions, where you can add new code. The bottom there, we have namespace A, namespace n, and a foo function inside that. And Baz is going to call a : macro, right? So macro on the bottom is going to expand to n : foo. So Baz is going to call a : n : foo. Everybody following? Okay, so on the left, because we're retrieving precise information, we have that Baz calls a : n : foo, whereas bar calls n : foo, right? I should just say a n foo and n foo or something. I don't know. This is getting a lot of colons in here. But on the right, if we collect that stuff, we're going to end up with n : foo inside the macro, pointing to 2 namespaces and 2 function foos, right? And in fact, this is fine for code navigation, because when I command click on foo inside the macro definition, and my ID says, hey, this is expanded in such a way in your code that it refers to one of these foo functions. I'd be like, oh, great. Why is this being expanded this way, right? But if I try to build a static analysis tool with the cross references on the right, and you tell me that bar calls both foos, right? Because if we assume bar invokes macro and macro invokes both n : foo and a : n : foo, right? Then we're gonna deduce that bar calls both of those foo functions, which is not true. And so precision matters for these kind of analysis tools that like linters are built on top of, right? But heuristics are fine and perhaps desired for code navigation. Okay. So we're gonna talk about Angle. This is the schema defining / query language for Glean. And so I'll basically have a full example of a tiny language that kind of looks like C++. So predicates and facts. These are the core of what Glean deals with. So facts are effectively data. You can think of them as values. And the types of those facts are what's called predicates. So we're going to define a bunch of different predicates, and we're going to have different instances of those predicates, which are kind of like a type and value, where you have a type and a bunch of different values of that type, right? So we're going to have a bunch of facts of a certain predicate. Okay, so this is example.angle, and we're going to basically write a schema for this example language. So predicate name : string. So that's defining a predicate called name of type string. So it's going to store a value of type string, and we're going to retrieve. We're going to name it name so that we can store different names in the language, and then we can retrieve it later. I'll show specific JSON corresponding example of the data. Qualified name is going to store a name and a namespace. So in real C++, this would actually be, like a list of namespaces, right? Because you can have a : n : foo. But let's say for this example, we're just gonna say you can only say like n : foo, and that's it. Okay, so predicates are types of facts. I already said that. Each fact is assigned an ID. Unique facts are stored exactly once. And so what that means is we're going to deduplicate any fact that we see multiple times. And why is this important? We're going to have a farm of indexers that, so we're going to have, like, let's say, a bunch of machines, right? Indexing C++. It's going to come across the same entities over and over and over again. Like even, in fact, even within the same build, you're going to say, for example, optional.h, right? You're going to have all these translation units that include optional.h transitively, and those are separate builds, right? We're going to come across optional.h probably tens of thousands of times, and we don't want. We want to be able to consolidate all those duplicate views of optional and collapse into the exact same to a single fact. And facts are stored by prefix for efficient queries. And I'll get more into what that means a bit later in the presentation. Okay, so here's an example program that we're going to index. We're not even going to index all of that, but we'll do a little bit of it. Excuse me. So this is what you writing a Clang tool looks like. So in a part of the Clang library called recursive AST visitor, you can override a function called visit namespace decal, and this function is going to be called when the Clang AST during the traversal comes across a namespace declaration. Okay, and we're not actually indexing the namespace itself. We're literally just indexing the name of the namespace and then saying, okay, we've indexed something of that namespace. Okay, so okay, let's walk through a little bit more detail. So decal arrow get name, that's part of Clang. So that's part of Clang. That's going to give you the name of the namespace. db.fact, that's a utility library that we have in Glean that we provide you. And so you can have a database and you can call .fact on it, which is going to like write out that fact and send it to Glean, right? Example : name is generated by Glean based on the angle schema, and it's available to you through Glean/lang/clang schema.h. So that's going to write the fact to Glean, and in fact, as a result of that function, as a result of that call, you're going to get a handle to that fact, and I'll show an example of where we use that in a bit. But this is basically just writing out the example name predicate, an instance of the example name predicate, and writing the fact to Glean. Okay. Sorry? That's exactly right. So this is the JSON representation of the data that gets written to Glean. So, and okay, I'm cheating here because I don't really want to write the qualified name stuff, and we don't have that much time. So these are what qualified names would look like if we were indexing them as well. So the first part here is the ID, right? And what I said earlier is that each unique fact gets an ID. And so these are the IDs assigned to these facts. And we have these IDs that are inside of qualified name. And these IDs are references to existing IDs. So we can refer to, so qualified name refers to name, which is a predicate itself. And so we can refer to other predicates, and referring to other predicates, or other facts, I should say, is effectively a pointer reference, right? Because we just store the fact ID as opposed to the fact directly. Okay. And so qualified name, for example, n : widget and 2 : widget, the widget part is shared in the database. Okay, let's keep going. So Glean comes with an interactive shell. And so if you have a database, you can spin up a shell and try it out. And so this is where the querying part comes in. And let's see some examples. So when you spin up the shell, you're going to get the name of the database. And I named the database example because we're indexing example. On the left, you're going to have the predicate that you want to query. And then on the right is going to be a pattern. You're going to describe the shape of the thing that you're looking for. And Glean is going to scan the database and yield facts that match that pattern. So in this example, underscore is underscore, like in pattern matching anywhere. It's going to match everything, just anything, right? So this is going to dump out all of the example names that we saw in the previous slide. You can also specify, for example, in qualified name has a name and a namespace, right? And you can provide parts that you care about, right? So you can provide, for example, name is widget. It's going to produce the two namespace. The two widget qualified names that you have in the database. You can also use the vertical bar, which means or. And so again, on the left you have example.name, which is the name of the predicate, and then on the right you have a pattern, which is n1 or n2, and so that's going to give you the two n1 and n2 names in the database. Does that make sense so far? I hope everyone's following. Okay, I see some nods. All right. Okay, so let's keep going. This is building on the example that we've been working with. So on the first line there, we have type kind. It's going to be an enum of struct, class, and union. Those can be any names, but these are ones that correspond to our language. And then a predicate called record declaration, which is going to have a qualified name, a kind, that's going to be struct, class, or union, right? And then the location of where that record declaration is. So for now, we're just going to store the file and the line. And so there are a few different built-in types that come with Glean in Angle, and string and nat are part of those built-in types that are available. Okay, and the record decal indexing is going to be a little more complicated, but again, we have the recursive AST visitor from Clang, visit CXX record decal. We're going to grab the name part, and we're going to construct the qualified name. Okay, so the first line, you've seen that code before, right? So db.fact, example name, get name. that's going to write the name fact, and then give you the handle to that fact. So because we're going to come across names multiple times, right? And what I said about deduplicating unique facts, that's going to be deduplicated, no problem. Okay, we do the same thing for the namespace name. We need to do some more work to like retrieve the namespace name because we need to get access to the decal context, blah, blah, blah. Those are kind of Clang AST details. And then we're going to produce this composed fact, qualified name, which takes name and namespace, which are the handles that you got back from calling the fact function. So then the Q name itself is also going to be a fact handle, and then you can ultimately pass that at the bottom there. So here we're getting the tag kind and figuring out which kind of record we have, and then at the bottom we build the final fact that we want to write out to the database for record declaration. So Q name, kind, and then the file and line number that we're going to retrieve that I omitted here. And so this will produce something like this. So record declarations again get assigned new IDs, and then the stuff inside. So this name is a reference to existing facts, right? And then you can see for the N1 widget, the kind is class on line 2, and then for N2 widget, the kind is struct on line 6, right? And so this is how we start to build up the information about 10 lines of code that we have on the left there. All right, so let's keep going. This is probably going to be the last iteration of where we go through this example. So xref is going to be two parts. One is the target that we're pointing to, and lines is going to be where those references are coming from. Okay, and file xrefs is going to be a file and then an array of those xrefs. So the square brackets there mean array in Angle, and it can, just a list of stuff, right? And so we're going to collect all of these xrefs from a single file and store that into file xrefs. And so the way you use that, sorry. So this is the data that we're going to store. So in file xrefs for file widget.cpp, we're going to have xrefs where the target is n1 widget, and the lines will be 9 and 10, right? So those are the variable declarations that refer to n1 widget. We're going to have two references, but it's grouped into this single xref to n1 target widget rather. I see people looking intently, so I was giving it a minute. Okay, let's move forward. So earlier I showed the Glean shell. You can do similar thing with Glean query, where you can basically give it file xrefs where the file is widget.cpp, right? And based on the fact that we wrote before this slide, this is the information that it's going to spit out at you. And by default, the Glean command line stuff will like expand all of the nested facts so that you can kind of see it without having to chase those pointers, basically, right? Okay, so let me take a sip of water. So at this point, we've seen a bunch of different ways for indexers to actually like manually produce these facts, right? And we need a lot of that to get our basis. But there's a layer where we can derive new facts, and so we'll get into that just after I take a sip. Okay. Okay, so I'll show you this example. It's called file to file. So the setup is exactly the same as before. We have the xref, which points to a target. We have file xrefs, which is has a file and the xrefs in that file, right? And what we want to do is, I don't actually care about all those individual targets that we're pointing to. I just want to see if there are any references to other files, right? So this is going to be a derived predicate. So first we're going to define the predicate. So the predicate is file to file, from string and to string, right? So that part's relatively simple. That's just the shape of the data that you want to see. Now we're going to write code that that communicate like how to produce that fact, right? So we're gonna say from and to, and these are logic variables that get introduced. The capital F and capital T variables are the ones that we're gonna be returning. So the where is where the logic starts. So we're gonna say scan through the file xrefs predicate and grab the file and the xrefs, and the xrefs square bracket dot dot notation is iterating over the array. So it's basically expanding the array. So for each element in the array, I want to grab the target and the file within that target, right? So we're looking at the file that the target is defined in, right? And we're gonna set that as the to variable. And so, okay, so this example is gonna be kind of silly because we only have references to ourselves, right? And so widget.cpp is only going to go to widget.cpp in this example because all of our xrefs are pointing to within the file. But let's say we have xrefs to a.h and b.h, then this predicate, based on those specific data, going to produce a.h and b.h as the result of this deduction, this derivation, I should say. Let's do another example. We're going to reverse the file xrefs schema. So target uses will be a predicate where, given a target, we're going to give you basically defined references of that target. And the way we'll do it is we're going to take target, file, and lines. And so the order of these things matter because that's the order in which they're going to be indexed in. But I'll show you like why this matters. Okay, so we're going to take target, file, and lines. Okay, we're going to iterate over the instances of file xrefs that we have, and we're going to bind file and xrefs like before. And then we're going to iterate over the xrefs, and we're going to flip the order of this. So the target, even though it's on the other side of xrefs, we're going to pull it to the front, right? And we're going to collect over all of that. And so concretely, we end up with if we do a query on target uses on a specific like N1 widget target, right? It's going to basically scan through all of the xrefs, and every time it finds the target, it's going to reverse the xref and then collect that so that we can see N1 widget is referenced from widget.cpp lines 9 and 10, right? Now, as I said, like this is going to actually iterate over every file xref and xrefs to compute this every time, because the derivation by default is done on demand. And so this is the derivation rule that we've described, but the execution of it, it's going to be executed every time, right? And so to get around that, what we do is what we can add is a stored keyword in that position. And what that means is Glean is going to then, upon doing this execution, write the facts actually into the database, right? So before, without the stored keyword, it's going to compute the facts on demand. Nothing's going to get written to the database. With the stored keyword, it's going to get written to the database. And so now when you do that query, it's going to be fast, right? And the reason why this matters is because the predicates are, the facts in the database are sorted by prefix order, right? And so if you provide the first fields of a predicate, then the queries will be fast. But if you specify later fields, then it's going to have to do a whole scan of the front fields to find those. And so doing this reverse indexing effectively is useful in a lot of cases, but we don't do it by default because we don't need it for everything, and we don't want to pay for that if we don't need it. Okay. Right. So let's see. How do I explain it? So okay. So let's say, for example, let's go back to a real example, another real example, right? A simpler one, perhaps. Uh, so okay. So let's say the qualified name thing, right? So qualified name has the name and a namespace, and so, but it's indexed in order of the prefix. And so if you have a specific name that you want to look up, then you can provide the name field, and it's going to find it as soon as it finds it in the order in the database, right? But let's say you want to specify the namespace. Because the namespace is on the second is a second position, it's going to have to look through the entire thing to find the corresponding thing. Whereas if you flipped the order, and now it's indexed by namespace effectively, then the lookup will be much faster because you can find it. Because that's the tuples in the database are effectively sorted in prefix order, and so you can do log n searches per column effectively, right? And it goes left to right, and so the earlier you can make the thing that you want to do lookups by, the faster your queries will be. But in a lot of cases, it actually doesn't matter that much, and so that's why we don't index everything by every position. Yeah. I hope that was clear. Maybe we can do better. Okay. All right. Let's get to. Okay. Did that? Okay. So that showed a lot of like how we derive new facts from existing facts. This part is showing the code markup layer. So remember earlier when I said we're going to have multiple schemas, one per language, but we're going to provide this like code markup layer, right? So in Angle, you can import the per language schemas by using import. Assume we have something for CXX and hack. We're importing our own example language that we've been working on so far. And the code markup layer, the file xref, is going to be language agnostic, right? And so the target, rather than being a record declaration like we had before, is just going to be a file location, right? So we're losing information, but it's good enough for a code navigation system to query this predicate and say, okay, if you start from here, then go to the file location on the other side, right? All of the semantic information about each of the languages are stripped away here, but that's fine for a language agnostic tool. And so we're going to use the derivation stuff that we've been working with, and we're gonna say, okay, this is the code for the example language that we've been working with, right? So we're gonna take the file extracts, and the details of this actually isn't all that important, but we're gonna OR that stuff, the results of this, with all of the languages that we support. And so C++, for example, we have a file xrefs, something like we've been building together, but there's also a pp xrefs, which is a preprocessor xrefs for macros. There are also like declaration to definition and back cross references, and all of these things are separate predicates. And so you can actually like provide all of those. And like the point is that different languages will probably have slightly different logic in providing how to derive this predicate, but that's fine. On the client side, they don't care, right? And realistically, what we do, what we do in reality is we create a code markup .language file, and then we basically like hide all of this will be in code markup.example hidden into a code markup.example file xref, and that's going to basically just do that. Like it's kind of like calling a function, right? And you encapsulate all the complicated logic behind that language that knows how to do the exposing of its own language. And so this is in reality kind of like what it looks like. Okay, now the fun part, handling C++ macros. So I showed like a snippet of the complexities of it earlier, right? With like the precise information versus like what code navigation wants and stuff like that. So let's get down to kind of the nitty gritty here. So there are effectively 3 types of locations in C++. One is file, second is expansion, and the third is spelling. So file locations are basically the non-macro locations. There are no macros involved whatsoever, right? So foo function here, for example, and the invocation of foo are not involved in a macro at all. These are located in file. These two are invocations of macros, and so these are what's called expansion locations. And the macro argument, as well as the macro body, have spelling locations. So these are locations where like it doesn't really exist because it's gonna get pasted into somewhere, but it's physically where it's spelt, and so it's called spelling locations. And macro arguments fall into that category because it's gonna get passed into the macro and then it's gonna get pasted somewhere, right? Okay, so effectively what we need to capture is references between these 3 locations to each other, right? So file can point to file, and every way in which in between. And so let's see some examples of that. So this is the simple example, right? We have no macros at all, file to file. We have some examples where the definition is in, like the declaration, I should say, is inside the macro. And so when you paste it, it produces the declaration. And you see this all the time, right? If you use G flags, defined flag does this, right? In fact, it declares a lot more than this, right? And then you're going to refer to it by like flags underscore name or whatever, right? And so this is going to be a file to spelling location. And in fact, the spelling is a macro argument, not a macro body. Okay, let's get to some more stuff. So here we have a spelling in a macro body to file. So now we're like escaping macro definitions to normal code, right? And here we have spelling location, which is a macro argument that points to a file. And finally, if you've seen code like this, you have code that points within itself, within the macro definition, right? And so we have spelling location referring to spelling locations, both in macro bodies. But again, like this code, this text has no semantic meaning until it's pasted somewhere, right? And so most code navigation systems, when you try to do navigation in this area, it's just either gonna give up and not do anything, or you'll get some results, but it'll be based on a textual search nearby tokens and stuff like that. Okay. So this is kind of horrifying macro code. Let's walk through it together. It's from a Facebook project called McRouter. So we have a macro called stat. Take some parameters. One of them is called underscore data assignment, right? At the bottom of that stat macro, you see s.data space underscore data assignment. Okay. When you look at the use of stat on line 271, the last argument is .uint64 equals value, right? So that's not named parameters. We don't have named parameters all of a sudden in C++, right? This is .uint64 equals value. That text being passed into the stat macro, getting pasted where data assignment is on line 269, and ultimately you're going to have s.data.uint64 equals value. Horrifying, but hopefully you're following what I'm saying. And yes, but would you know that just by looking at it? So So the question is like, in your experience of writing or like using C++ tools, if you go to definition on UN64, would you expect that to work? Have you like, has it been your experience that it works or not? Yeah, I heard no right away. um, and yeah, and so like this is the kind of stuff that people have to like unravel the macro to figure out like what is even going on here, right? So this is a little demo. I'm gonna play it. I'm gonna go to the definition there. We're gonna jump straight to this union. We're gonna click on data, which is the union that Chris was talking about. Right? We're gonna click on S, which is a reference to S within itself, and it did that jump. I don't know if I don't think that was actually quite obvious, but when I clicked on S in s.data, it jumped to the declaration of S on line 264. And so that's the spelling to spelling that we were talking about with which is like stuff that looks like code within the macro definition that's not really code until it's pasted, right? And so this demo is built with Glean as the backend code indexing service on an LSP that reads all of the xrefs from a file, like basically like the file xref predicate that I showed you. When we open a file, we make a request to Glean, say, get me all the xrefs in this file. We're gonna cache that, and when go to definition requests come in, we're just gonna look up in that map to see where we need to go and do the jump, right? And so this means that like Glean can also power, for example, like web browsers, web code browsers, or if you are on a local machine and you have no checkout of that code at all, right? Because it has the data. Yeah, I mean that's basically it. I feel like I wanted to say something more. Oh, one more thing. So basically, the macros, as I said, like it doesn't have any meaning until it's pasted, right? And it's going to be pasted in a lot of cases, like hundreds of times across many files. But again, because Glean will deduplicate those facts, as long as you set up your predicate in such a way that the same facts will get deduplicated, you can index it how many ever times you want across how many ever indexers, and it'll collapse for it to be queried efficiently. Yeah. All right, that's everything. Thank you. I guess we have some time for questions.
Yeah, who has a question? All right, all the way in the back. One over here.
So I would like to get a sense of the amount of effort involved in adding support for another language to this entire. This is obviously a very complex system. So let's say that someone wanted to add support for Ada, or for Lisp or APL, or how much effort would be involved in that?
Right. So the answer will depend. So there are kind of two answers. One is, if there are no indexers out there that already do the work, then we'll have to go through basically what we walked through of like designing the predicates for how to efficiently store the data about that language and all that stuff. That's a lot of work. What we've been doing actually to support these different languages, so there's a company called SourceGraph that also does code indexing as their day job. And they have a schema called SCIP. That's SCIP. And that's basically like a least common denominator schema that I was describing earlier, that you can use to power a lot of the simpler, like not simpler necessarily, more language agnostic tools, right? And because our schema is very flexible, we actually put together a skip schema. So any indexer that produces skip data, according to that schema, we can actually ingest into Glean, and you can start playing with it right away. And so this is actually how we support JavaScript. I believe there are a couple other languages that a TypeScript as well. TypeScript, there's a source graph skip TypeScript or skip producing TypeScript indexer, which we use to produce the skip facts, which we then translate into Glean facts, the Glean version of the skip schema, and then we start querying with that information. Yeah.
Can you handle old path?
So we do some of that. I don't know how it's done. So the reason I say that is because I know the Python indexer gives me a bunch of information that I don't know how it gives me. But that stuff is, yeah. So right now our indexing, I don't think would capture that stuff, but it probably could. Yeah, because for example, like you can it's not really restricted to like language front ends for the indexers, right? You could have like test infrastructure or like build systems that upon building an artifact produces facts about how long it took to build that artifact, and be able to do a very interesting analysis with that stuff. So as I said, at the core of it is it's another database, right?
Did you make your own LSP server using this, and is it open source?
Oh, hey. Yeah, so the reason why this is a screenshot is because the LSP that we built is not open source. But we'll see what I can do.
So code obviously isn't like static, it mutates over time. How do you deal with the mutations? You mentioned there are stored predicates and facts.
Could you say that again?
So I imagine you have a giant mono repo, right?
Yeah.
So do you sort of index the repo over time? And if so, like, how do you handle, I write a commit, the former predicates may no longer be true. Like, how do you sort of invalidate those and keep things?
Right. So until recently-ish, we just indexed the entire world every time, and we just periodically indexed a commit, like the entire code base at a specific commit, and then served that, and that would over time just kind of get updated, right? And so we were always a little bit behind of whatever main branch that you might be on. Now we actually have what's called incremental indexing in Glean, and so you can actually look at the files that's changed, and then produce the set of files that we need to reindex, right? Or the files that changed, and then we need to figure out the dependencies that that tells us like all of the files that we actually need to reindex, and we'll invalidate like existing facts. And this is the details of it. Actually, I don't know that well, but my understanding is that there's a notion of ownership of different facts, and like typically it belongs to a file or something like that. And then if that file is invalidated because it needs to change, then we're going to invalidate all the facts that are owned by that entity, in this case a file. So that's how we like invalidate old facts and write new ones. And this way we can actually, like, the invalidation just hides the old facts, and so you can get multiple views, right? You can get like multiple views of the same DB, right? Because maybe you want to actually look at some old code, right? Maybe you want to go back to a revision and do navigation there. And so by layering the data on top and not deleting it, we can actually provide like multiple views of the data over time. But there are some limitations to it, and it's relatively recent work. So, but it certainly like sped up the entire indexing process quite a bit for us. Yeah.
Very cool.
Yeah.
Thanks.
You're welcome.
All right. We have time for one more question. Well, actually, I have a question. So
Okay.
I really enjoyed this talk, and I really wish there was just another 30 minutes to hear you talk about this some more. So, is there somewhere I could go to listen to a 30-minute version longer, 30-minute longer version of this talk?
Yeah. So I'll be giving this talk at C++ Now in a few weeks. So that'll be end of April, beginning of May. Yeah. So you can see the 90-minute version of this talk either come to the conference or you can find it on YouTube afterwards.
All right. Good stuff. All right. Well, let's thank our speaker. Oh, we got.
Is there
What?
one more question?
So, is Glean open source?
Yes, it is. Yeah.
So basically, anyone can download and to try to play with it.
Yeah. So we have a Docker image that you can pull and play with. It has like a flow code base that's packaged with it that we have already indexed or something, so we can like query different.
I understand, but the interesting experiment is to try to index my own code base.
Yes.
and
Of
see
course.
how that works. Do you have any kind of performance metrics as to, a rough indication of the amount of time it takes to index 1 million, 10 million, 1 billion lines of code? Or
Yeah, so I need to do that experiment with like the open source version and like do my own experiments for that. I don't feel all that comfortable sharing some of the numbers that I do know of already internally.
Maybe you buy him a drink and he'll
No, I'm just saying. I'm just saying, like I can share those numbers once I do the experiment myself with the open source version. Is what I'm saying. I haven't tried it. No. Yeah. What percentage gains? Well, sometimes it's. Yeah, sometimes it's like 5 minutes for Clang D to spin up and index everything that's relatively like related that's needed versus like, I don't know, 10 seconds, right? I mean, it's like 10 seconds is literally like pulling pre-indexed data and then serving it. Like it's probably less than 10 seconds. But yeah.
All right. So let's thank our speaker again.
Thank you all.